My dear students, welcome to my channel. In this class, we are going to discuss the remaining crystal defects. In the last class, I had told you that the defects in crystals have been broadly divided into point defects and line defect. The point defect is due to the deviation from the ideal arrangement around a point, and a line defect is due to the improper arrangement or deviation from the ideal arrangement in entire row of lattice points. So a point defect is around a point, and a line defect is due to the defect in irregularity in the arrangement of entire row of lattice points. I told you that the point defect is divided into stoichiometric defect, impurity defect, and non-stoichiometric defect. What is a stoichiometric defect? The defect that does not cause any change in the stoichiometry of the compound, or the defect that does not disturb the stoichiometry of the compound is called as a stoichiometric compound. And in stoichiometric defect, there is vacancy defect and interstitial defect. I told you that the vacancy defect is due to the absence of a point in its lattice site, and interstitial defect is due to the presence of a point in the interstitial site. But these vacancy defect and interstitial defects are found to be in non-ionic compounds. But in order to have electric neutrality in ionic compounds, the same defects are observed like Frenkel defect and Schottky defect. I told you that in Frenkel defect, one of the or some of the cations will be migrated to the interstitial site, and in Frenkel defect there is no change in the density. It is also called as a dislocation defect, and I told you that it is observed in the ionic compounds with low coordination number. If you go for Schottky defect, that is due to the missing of both anion and cation. That means here equal number of anions and cations are missed from the lattice. Because of this, the density will be decreased. This is observed in ionic compounds with the high coordination number. But silver bromide will be showing both Frenkel and Schottky defect. This is what we had learned. But this number of the Schottky defect also very prominent. I mean that if you take NaCl crystal, there will be 10 power 6 Schottky pairs for 1 cubic centimeter volume. If you take 1 cubic centimeter of NaCl crystal, that will have 10 power 6 Schottky pairs. Let me explain. If you take NaCl crystal, in 1 cubic centimeter there will be 22 ions, 10 power 22 ions per cubic centimeter volume. But for every 10 power 16 ions there will be one defect. For every 10 power 16 ions there will be one defect. That means in 1 cubic centimeter the number of Schottky pairs will be 10 power 6. That means they are very prominent. There will be considerable number of defects in crystals. Now let us move to the next defect. Next point defect is impurity defect. What is meant by impurity? Any particle or any unwanted particle presenting in a crystal, nothing but unwanted substance. For example, NaCl crystal is expected to have only Na plus and Cl minus ions. If any other ion other than this is present, then it is called as a impurity defect. In fact, if you take NaCl crystal, it will have Sr plus 2 strontium ions in them as an impurity, so it will cause an impurity defect. During the formation of NaCl crystal, the small amount of strontium chloride is present, the strontium ions from that strontium chloride will occupy some of the lattice sites of the Na plus. Originally Na plus should be there, but the lattice sites of Na plus will be occupied with the Sr plus 2 ions. Let me explain here. This is actual Na plus and Cl minus ions. So here just I am showing the impurity defect in case of NaCl. So these are Na plus ions, and here we have Na plus and Cl minus ions. So this is Na plus and Cl minus ions are present here. But what I said here, this is what the ideal arrangement, non-defective crystal here. But in this crystal, what happened during the formation, some of the Na plus ions, for example, say here, this is Na plus and this is also Na plus ions. The sites of Na plus ions is occupied by Sr plus 2 ions. Sr plus 2 means nothing but a strontium plus 2. Look here, I am writing here Sr plus 2, that is nothing but strontium plus ion. What happened? In the lattice site of Na plus, Sr plus 2 is present now. Now it is defect. This defect is called as impurity defect. But not all these sites, vacant site will be occupied by Sr plus 2. Why is, the charge of Na plus is 1 unit positive charge here. But if you take Sr plus 2, 2 units of charge here. Only 1 unit of charge here. That means 2 sodium plus ions equals to 1 strontium plus 2 in terms of charge. So that here we have missed 2 positive charges. So that is replaced by 1 strontium ion, because 1 strontium ion will have 2 positive charges and the other one will be left vacant. So this is called as impurity defect. So impurity defect is due to the presence of ions, unwanted ions in the lattice points. So for example, if you take molten NaCl, that will have small amounts of strontium chloride, that strontium ions will occupy the lattice sites of Na plus to give rise to an impurity defect. Even you can observe this defect in case of AgCl. AgCl, the impurity will be cadmium chloride here. The Ag plus ions will be occupied by the Cd plus 2 ions, cadmium ions. So it will cause an impurity defect. So here, number of vacancies will be equal to the number of strontium ions. For example, if 2 strontium ions are there, 2 vacancies will be present in it. 5 strontium plus 2 ions are there, 5 vacancies will be left here. So this is all about impurity defect. So impurity defect is due to the presence of impure ions, that is other ions in the lattice sites. It will occur usually during the crystallization. Now let us go for the next point defect, that is a non-stoichiometric defect. The next point defect is a non-stoichiometric defect. What is the stoichiometric defect? The defect that does not change the stoichiometry, that does not disturb the stoichiometry. Stoichiometry means that the ratio of the different elements. NaCl means its stoichiometry is 1 Na and 1 Cl, 1:1. So after stoichiometric defect, there will not be any change in the Na and Cl. The ratio will not be changed because of that defect. But here, because of the defect, the stoichiometry will be disturbed. The point defect in which stoichiometry will be disturbed. Stoichiometry will be disturbed. The defect by which that stoichiometry will be disturbed is known as a non-stoichiometric defect. To understand it, for example, take FeO. ferrous oxide. So what is the stoichiometry here? One iron is bonded to one oxygen here. Fe plus 2 is bonded to O minus 2 here. So this is the stoichiometry. But because of the defect, it is found that in FeO, the Fe is 0.93 to 0.96 only. It is less than 1. One Fe should be having one oxygen. That is the ratio. But here if you observe due to the defect, what happened here? One oxygen is having only 0.93 to 0.96 of iron. Even not 1, less than 1. So that ratio is disturbed here. Stoichiometry is disturbed. This is the correct stoichiometry. There is no change, 1:1 ratio. But here it is disturbed here. Now that ratio is affected here. It is not 1:1. 0.93 is to 1. Or 9. It will be varying from 0.93 to 0.96 due to the non-stoichiometric type. Let us discuss. First of all, basically you should understand that non-stoichiometric defect causes change in the stoichiometry of the compound, or it will affect the stoichiometric composition of the compound. Now, why it changes? For example, if equal number of anions and cations are mixed, there will not be any change in the stoichiometric composition. Take a Schottky defect, that is one of the stoichiometric defects. There equal number of anions and cations will be missing from the lattice. So there is no any change in the stoichiometry. Even if you take Frenkel defect, their cation is moving to the interstitial site, but still the number of cations and anion ratio is not disturbed there. In Schottky defect also, equal number of anions and cations are moving, so that the stoichiometric ratio will remain same. But here it is different. Now let me explain. The non-stoichiometric defects are again divided into two major types. That is a metal excess defect, and the other one is a metal deficiency defect. For example, our body should have a minimum number of minimum quantity of all vitamins. If they are more, they will cause some disorder. If they are less, they will cause some disorder. So defect due to metal excess, stoichiometry may be affected. Due to the deficiency of the metal, stoichiometry will be affected. To understand in an easy way, for example, take a classroom. Imagine that there are 25 girls and 25 boys. Now what is the ratio? 1:1. Now the ratio will be disturbed. That means stoichiometry will be affected. How it will be affected? For example, one more boy has joined the class. Now the boys ratio is 26 and girls is 25. Now the boys number is 26, girls number is 25. Now the ratio is not 1:1. Stoichiometry is disturbed because of the extra boy who have joined. Or let us imagine that there are 25 boys and 25 girls. Now one of the girl is absent. One of the girls is absent. Now what happened? Boys is 25 and girls are 24. Now also the ratio is, composition is affected. Stoichiometry is affected. That means even if an extra boy comes, the number of boys will be more. Even one girl is absent from that class, the number of boys will be more. So that here, the stoichiometry will be disturbed due to the presence of metal excess defect. If excess of metal is present, that will affect the stoichiometry. Even the deficiency of the metal. If the metal ions are also decreased, then also there will be disturbance to the stoichiometry. This is the broad explanation. Let us go into details here. First, we will discuss a metal defect, metal excess defect. Now we are going to discuss a metal excess defect. Later we will discuss the metal deficiency defect. So non-stoichiometric stoichiometric defect is of two types: metal excess defect and metal deficiency defect. Now this metal excess defect will be again of two types. That is metal excess defect due to anion vacancy. Anion vacancy. This is the first type, metal excess defect due to anion vacancy, and metal excess defect due to extra cation. Now let us go into the metal excess defect. So later we will discuss metal deficiency. So metal excess defect is of two types. So that is metal excess defect due to anion vacancy, and metal defect due to extra cation. Now only I told you that one of the boys is joined the class, the stoichiometric composition of the class will be disturbed, or one of the girl is absent, now the stoichiometric composition of the classroom will be disturbed, the ratio will be affected. In the same way, if anion vacancy, that means if one anion leaves the crystal, there will be a more number of cations and it will affect the stoichiometry. Or extra cation, if there is an extra cation, then more number of cations and less number of anions, then the ratio will be affected. The ratio will be changed. Stoichiometry will be changed. Let us discuss in detail. Now let us go to the metal excess defect. The first type of metal excess defect is metal excess defect due to the anion vacancy. If you understand the title, if you see the title, you will understand what this defect is. So what is the first type of metal excess defect? Metal excess defect. Metal excess defect. Here metal is excess. What is the reason? Due to anion vacancy. That means anion is leaving and creating a vacancy. This is called as a metal excess defect due to anion vacancy. Let me go for the definition. In metal excess defect due to anion vacancy, the anion will leave the lattice, creating a vacancy or creating a hole. When anion leaves, the site will become vacant. That hole or that vacancy will be occupied by the unpaired electron. This is called as a metal excess defect due to anion vacancy. That means anion is leaving here from the lattice, so that there is a vacancy. That vacancy will be occupied by unpaired electron. So how it occurs and what is the consequence, let us understand. Here also we will take NaCl, we can take here. So just now I had drawn here. NaCl consists of Na plus and Cl minus ions. So here we have Na plus and Cl minus ions in NaCl. See here. Now these are Cl minus ions. So this is the ideal arrangement of the particles. Now what is a metal excess defect due to the anions? I told you that one of the anions leaves a vacancy, the anion vacancy, defect due to the anion vacancy, and this vacancy is occupied by an unpaired electron here. This is an unpaired electron, and this defect is called as a metal excess defect due to anion vacancy. The defect in which anion leaves the lattice site, forming a vacancy or a hole, and that hole is occupied by the electron. Here empty space is there due to the absence of Cl minus, but that is occupied by an electron, and this defect is called as metal excess. Now extra metals are there here. If you see here, anions are less now because anions has left. Metal is excess here. Stoichiometry is disturbed, but metal ions are excess, so that it is called as metal excess defect. But the reason for it is due to the anion vacancy. Now this center which is occupied by the electron, or the anion vacancy occupied by anionic site occupied by the electron, is called as an F center, capital F center. What is meant by F center? Actually it is from the German word. F means for Benzenter. F means for Bengenter. That means color importing, color giving. The word means that color giving. This unpaired electron presencing in the crystal will cause or important color to the crystal. So I will explain in detail why it is occurring. And so this is what basically metal excess defect due to anion vacancy is. Now I will tell you when it will happen. For example, we will take a sodium chloride crystal. Let us, it is an ideal crystal. That means Na plus and Cl minus are arranged as per the regular arrangement. Now when I expose these NaCl crystals to sodium vapor, just I am exposing these NaCl crystals to sodium vapor. What will happen? In sodium vapors we have sodium atoms. Those sodium atoms will lose electrons to form Na plus and that will combine with the Cl minus from the crystal. See that we have exposed the NaCl crystals to the Na vapor, sodium vapors. The sodium vapors will take Cl minus from the crystal. So Na will change into Na plus by losing an electron. And Cl minus that is present in the crystal will attract that Na plus to form NaCl. So the electron lost by that Na in vapor will be occupying the vacant set here. So what we have to do? We have to expose it to Na vapors. When you expose NaCl crystal to Na vapors, what will happen? This Cl minus presenting here will go to the surface. At the surface, there are Na vapors, Na atoms. So that Na atom will lose an electron and it will become Na plus. What is happening here on the surface? Na plus. Na loses electron to give Na plus. And here from the crystal Cl minus is there. Now both will combine here. Na plus Cl minus will give us NaCl. This is from vapor. Vapor has Na and this electron lost by this sodium will be occupying the vacant site here. But electrically here it is neutral. So this is what happening here. So Cl minus ion moved onto the surface of the crystal and a hole is formed. That hole is occupied with the electron. Now you know where does the electron has come from. It has come from the sodium ion, from the vapors. Why? Because the vapor lost, the sodium atoms lost electron to become Na plus. That Na plus has combined with the Cl minus taken from the crystal. But why it is called as an F center? So please tell me what is this defect? So the defect in which some of the anions will leave the vacancy by moving onto the surface, and these holes or vacancies are occupied by the electrons. These electrons are called as F centers. But why these are called as F center? I already told you these will give color to the crystal. For example, if you take NaCl crystal, that will have an yellow color when you expose it to visible light. In the same way, if you take lithium chloride, that will show a pink color. In the same way, if you go for potassium chloride, that will show a violet color when exposed to visible light. Why it is happening so? Here you all know that this is an unpaired electron. So this is an unpaired electron. So that when the light visible radiation incidents on it, it will excite to the higher energy level, and while coming to the ground state, it will liberate the energy, and that energy liberated will be appearing in the form of color. That is why this trapped electron is called as an F center. So F center is nothing but the unpaired electron present in the hole or vacancy created by the anion. So why it gives the color I had explained. So this is all about the metal excess defect. Here metals are excess now because anion is left due to anion vacancy. Now what is the other defect? That is metal excess defect due to the extra cation. We will discuss in the next class. Thank you.